Let's take a look now at a very, very interesting topic, which is the idea of electrochemistry. It is arguable that electrochemistry is the basis for the 21st century. Electrochemistry explains something called a battery. So the basic idea behind electrochemistry is that when you run a chemical reaction, certain types of chemical reaction, you can cause electrons to move from one material to another. When these electrons move, we call that electricity. And electricity, of course, can be harnessed to do things for us, like run our cell phones, light light bulbs, and the myriad of things that make up this 21st century. So electrochemistry is chemical reactions that provide electrical energy under the right conditions. Now, in order to make that happen, we provide a wire between two substances that carry those electrons being released, and that is how we're going to allow ourselves to do things like cell phones and electric motors. When electrons are moving in that wire, we call it an electrical current. And of course, this electrical current is what is being used to do work, including our electric cars. Two gentlemen that were instrumental in the development of these ideas was Luigi, not the PC gain type, but Luigi Galvani and Alessandro Volta. There is something called a volt and a galvanometer that are used in electricity, and it was named after these gentlemen. What's the basis upon which all of this is going to be built? What's the basis for electrochemistry? And the answer is electricity is based upon oxidation and reduction, also called redox. Redox are a variety of chemical reactions that cause electrons to be released, and we can use that to cause electrons to flow. This penny is being oxidized and turning green because it's copper. So you're looking at an actual redox reaction. What is the basis for this? Well, you have a material A, and material A has some electrons, and those electrons are willing to be given up by it and loses them. But it's going to happen only if there is substance B. Substance B wants to pick up those electrons and gain them. Now, there are names given to this. When a substance loses its electrons, we call it an oxidation. When a substance is able to gain electrons, we call it a reduction. Now, this is going to get perhaps a bit dodgy. Substance A is called a reducing agent because it's responsible for the reduction process. And the reverse is true, of course. Substance B is called an oxidating agent because it's what's carrying out or causing the oxidation of substance A. We'll give you some tricks to remember what is what, but the bottom line is oxidation is the loss of electrons that you want to pay attention to, and reduction is gaining those electrons. The best way to remember it is that Leo goes grrr. What that means is loss of electrons is an oxidation. That's where Leo comes from. And then the gain of electrons is a reduction. That's the grr part. So if you remember that Leo goes grr, you can keep straight those two processes. Now, whenever we do these studies, we discuss what is called standard conditions. The standard conditions are the conditions under which we carry out these redox reactions. They don't have to be carried out at these conditions, but all our measurements are based upon them. In standard conditions, we have one atmosphere. It's 25 degrees Celsius, and the solutions that are involved are set at 1 molar. Again, these are the standards under which measurements get made. we can have our batteries and our cars and our cell phones not be in these standard conditions, but that will cause the results to be slightly different. So redox reactions are electrochemical processes. Let's make sure we're clear on that. The energy released by the spontaneous reaction, which means the spontaneous release of these electrons, that's what's releasing or producing this electricity. Phrased another way, electrical energy is being used to do a non-spontaneous reaction. Now, what does that mean? Well, imagine a light bulb. A light bulb on its own is not going to light up. Lighting a light bulb is non-spontaneous. So what we do is we hook up that light bulb to a battery, which is where redox reaction happens. Redox happens spontaneously. They will happen if we create the same conditions, and so we couple with a wire these spontaneous redox reactions to a non-spontaneous situation, which in this case might be lighting a light bulb. And that's how we get all these electrical processes to take place. Can you give me an example of this? Absolutely. If we take magnesium, a solid metal, and we take oxygen in a gas form, that reaction will happen spontaneously if you put those pieces together, and you wind up with magnesium oxide, which is a solid. Well, how do these pieces fit together? Well, in this reaction, what happens is magnesium is going to release or give up 4 electrons. That's an oxidation reaction. It's oxidation because we've lost 4 electrons. Remember, that's a Leo. Now, that event is referred to as a half reaction. That makes sense. Redox are 2 reactions combined. This is the first half, losing those electrons. Well, they have to go somewhere, and that's where the oxygen comes in. Oxygen is going to pick up those 4 electrons and become ionized. Well, the gaining of those 2 electrons is considered a reduction. And that is the second half of this process. You put the 2 processes together and you get a redox reaction. And notice there is a flow of electrons from the magnesium to the oxygen. And again, if you put a wire between these 2 things, we can conduct those electrons through the wire, which means we have electricity in our hands. Now, the initial value of magnesium is 0. Initial value of oxygen is 0. When we put it together, magnesium becomes a +2. Remember, there's 2 of them, so that's a +4 total. And then the oxygen becomes a -2, but again, there's 2 of them for a -4. So again, let's clarify. Half reactions are simply the oxidation side of things, or it's the reduction side of things. You put the 2 half reactions and you have a complete redox reaction. We always include the electrons when we show this, because after all, they're the ones involved in flowing. So the redox reaction are divided into 2 half reactions, the oxidation and the reduction. And to do that, we're going to have electrons flow. So let's take another example. We have copper solid, and that copper is sitting in a silver aqueous solution. From the reaction, you can see that the copper is going to be giving up those electrons and giving them to the silver. And we see now where these electrons are flowing from. So the oxidation side of this, remember Leo, it's going to be a loss of electrons. That's the copper becoming Cu+2. The reduction in this reaction is when the silver gains the electrons and becomes a solid. And therefore we have Gur, which is gain the electrons. You have then what's called an electrical potential. Now what that is actually not too bad. What that is symbolized by a E, capital E naught. And what happens is it's also referred to as a V-volt, named after Volta, which was part of the discovery of this. So what happens is the total amount of voltage, the total amount of electrical potential, the total ability to light that light bulb or move the car forward is a combination of the reduction and the oxidations. So let's take a look now at the reaction copper plus zinc make copper plus zinc ion. Now what happens here is the reduction of the copper, meaning the ability for the copper to pull those electrons toward it. That's a very good way of thinking about it. The copper pulls the electrons towards it. Its electronegativity is high. It wants those electrons. How strong does it pull? Well, it pulls by 0.34 electropotential. That's the reduction. Now, the zinc wants to give up those electrons. It almost like throws the electrons away. How strongly does it throw those electrons away? How strongly does it want to become oxidized? And the answer is it's 0.76. Now where these numbers come from at this point we'll not go into, but the larger the number, then the more likely the reaction is going to happen. So what is the total electropotential? What is the total amount of strength that these electrons are going to flow? And the answer is you sum the two up. So 0.34 plus 0.76, that's voltage. The voltage of the battery is how much the reduction is going to happen plus how much the oxidation is going to happen. And so the bigger the voltage, the better, if you will, the strength of the battery. So if the E naught of the reaction, if it's greater than 0, then we're going to take a look that the reaction in fact is going to happen. We're going to get an electron to flow. Now, that mixture is going to happen whether in fact you provide the wiring, whether you in fact use it to do work, you're going to get that reaction to go. So we have the notion behind now a simple battery, and that is what you're looking at here. This is a copper zinc battery. You have happening the gaining of electrons by the copper. That's where GR goes on. And you have the zinc, which is going to give up those electrons, and that's where the LEO comes in. It's a loss. So if you connect these two pieces of metal, and they're just strips of zinc metal and copper metal with a wire linking them, and we just put it in two containers that have an aqueous solution, we will cause electrons to flow. Why is it doing this? Well, two things are happening. What's happening is that the copper is pulling the electrons towards it. It wants those electrons for it. Zinc wants to push them away. It doesn't want those electrons. The result is you have this pull or push at the same time on these electrons. And that's why those electrons are moving through the wire. But we're going to run into a bit of a problem. And the problem is that we're going to start to get these negative electrons are going to stack up really quickly on the copper side. And eventually that stacking up becomes too great and the electrons stop flowing. We got to do something about that. It's the buildup of the electrons. So what can we do? Well, what we can do is create a salt bridge. Now what a salt bridge does is it provides electrical conducting between the two solutions. So what we have happening is it allows the current to flow. Now, the question you can ask is, why doesn't the electrons flow the other way through the salt bridge? And the answer is because the zinc plate and the copper plate are the ones that are moving the electrons. That's where the power coming from. And so you get a stacking up of the electrons on the copper side, and then basically by diffusion, you're moving those electrons through the salt bridge back again. So you have the electrons flowing only one direction, and that, ladies and gentlemen, right there is the basic design of all batteries that exist. Does it have to be copper and zinc? No. You can use lithium. You can use platinum. There's a wide variety of metals that will do redox reactions, and if you link them with wires, you can cause electrical flow. What's the basis for making a decision of what material to use? It depends upon the needs of the battery, in the conditions you're going to use them, the amount of voltage you need to get, and of course pricing of all this material. But that's the basic design of all batteries. It's based on electrochemical reactions. There's another way to build this thing, which is to put a porous disc. And it serves the same purpose of a salt bridge, except for, in fact, it's a bit more compact. And these are things you use more often in the kind of electrical devices we've got, such as the phones and cars. The porous disc serves a purpose as the salt bridge. You can still get electrical to flow. Now, one issue, watch this, it's kind of fun. You can see it very clearly. If in that wire sequence you put, for example, a light bulb, what happens is the electrons flow through the light bulb and the light bulb lights up. But you better keep the electrons flowing or the light bulb will shut down permanently. And the battery will in fact keep flowing and keep the light lit until the electrons stop flowing. This, in fact, is called a voltaic pile. It was the very first battery. And what you see is you have copper, zinc, all stacked on top of each other. And you have basically a salt bridge, which consists of the ion solutions. And, of course, the more you stack, the bigger the stack, the more voltage you can get out. Now, this kind of battery is very primitive, but it certainly worked. It's brilliant on the part of Volta to have developed it. But these things get heavy, really, really heavy. And so different designs and different materials allow you to change that up. So the basic design of a battery, the basic design of the battery is it has two electrodes, one that gives up electrons, the other one that picks up those electrons, gains them. They're usually metals. They're sitting in a solution where exchanges are taking place. One electrode conducts a half cell or a half reaction, and the other side is the other half cell or half reaction. Now comes some terminology. Reduction, where the reduction happens, is called the cathode. Where the oxidation happens is called an anode. So zinc giving up its electrons is called the anode, and the copper that's gaining those electrons is called the cathode. Now, how are we going to keep all of this straight? Well, first of all, we put the cathode where the half reaction of gaining electrons occur. We put that on the right side. That's just by convention. And we're going to keep this straight by reduction at the cathode. Red cat and ox. Red cat is reduction at the cathode, and an ox is an anode where oxidation occurs. So you have Leo goes grr, and you have the red cat and ox. If you're ever wondering, that's a red cat with an ox. You can never forget that. What are some of the ions that go into a salt bridge? Well, potassium nitrate is a common one. Now, because of that, sometimes batteries are rather dangerous because those salt bridges often contain acids. And therefore, battery acid, can become challenging and become a safety issue. But that material is what allows the electrons that move away from the zinc. The salt bridge neutralizes or stabilizes the charge. If you take away the salt bridge, then the reaction will stop. Now recognize that the copper and the zinc, you do have changes in the mass going on because of those reactions. And here's your final galvanic cell. On the anode side, you have oxidation going on. That's because there's an ox there. And as it happens, you'll notice in the big circle on the left, you'll notice electrons are moving away from the zinc. That produces the zinc ion. Enters solution. The electrons move through the wire. The voltmeter tells you how much voltage you have moving through that wire. The electrons wind up on the right side, and when you do that, you get the copper plus 2 is attaching or reattaching the copper to the surface, and that is going to be the red cat. These reactions will happen spontaneously, and because they do, they get linked by the wire through a non-spontaneous event, such as a light bulb. And that's the basis for batteries. It's based upon redox reactions. Again, cell potential. You're looking at the measurement of the voltage. On the left is an actual, very simple battery of the type we are familiar with. On the right is the copper. On the left is the zinc. The salt bridge links the two together, and you will notice there are electrons flowing because the voltmeter shows how much there is. Reminders that oxidizing agents pull the electrons, reducing agent pushes the electron. The sum of those two push and pulls is the overall electromotive force. That is the voltage, and it represents the cell potential. And again, the units are in voltage. The more positive the E naught is, the more easily the electrons are added, or more easily they are reduced. The more negative, the more easily the electrons are lost. Here is a chart that shows each of the half reactions, and these have been determined by experimentation. And so this is where the E naught or voltage measurements come in, and you'll notice on the left side, you'll notice there's reactions such as iron gaining the 2 electrons, its voltage is 2.87, etc. Notice the key issues here, that the half reactions, you could go both ways, but the sign of the reaction tells you whether what the strength is like. So sketch a galvanic cell of the reaction. Lead plus silver produces, tin plus silver produces tin ion plus silver. That is the diagram you would look for. You have the anode on the left where the tin is losing. You have the cathode, which is the silver on the right, where it is gaining with the salt bridge in between. And I will let you study that mind-bending experience as you start to understand better the electronic world that we live in.